In this video, we will check out 3 examples of solving non-homogeneous differential equations with constant coefficient. Recall that to solve a non-homogeneous differential equation, we have to first of all solve the corresponding homogeneous case and find its fundamental solutions. Next, we have to find a particular solution to the original problem. And finally, by using the superposition principle, we know the general solution to the non-homogeneous differential equation is going to be a linear combination of the fundamental solutions plus the particular solution. Example 1. For this equation, we have to first of all solve the corresponding homogeneous case, and we can use a characteristic equation. Recall that we just need to turn the order of derivatives into the corresponding degree of powers, right? And then we're going to end with a quadratic equation. And for this equation, you can use a quadratic formula to get the roots are going to be -1 plus or minus I. We understand for complex roots, the corresponding fundamental solutions are going to be e to the negative t. You understand the real parts goes to the exponent, right? And then we're going to have sine t and cosine t. We know the imaginary parts will give you the sine t and the cosine t. Next, we need to find a particular solution to the non-homogeneous case. And we need to address all the terms here, okay? But for the first term, we realize this is actually part of the fundamental solution. So to address this, we understand we usually have to give an extra t, right? By the way, when you have cosine or sine, your proposal has to contain both of them. So you're going to say the extra t here applied to both of the e to the negative t sine t and the e to the negative t cosine t. To address the second term in the right-hand side, we simply use the e to the negative t, the same thing. And to address the polynomial, we're going to use a polynomial of the same degree. Now we just need to find the coefficients a, b, c, d, and e. And to do that, we need to plug the y sub p into the equation. So you need to find the first and the second derivative of y sub p. Well, to find the derivatives, the first two terms, they are products of 3 functions. So we have to use a product rule. And here, if you consider the product of 3 functions, you have to take the derivative for each factor, right? And then multiply by the other 2 factors, and then you're going to sum them up, okay? So we just apply this rule to the first 2 terms. You can see the first 2 terms, each of them will give you 3 terms. And then for the rest part, the derivative is kind of easy to figure out, okay? So we just carry out the derivatives and we try to combine them. And then we're going to end with a simplified form like this. By doing the same thing, you can get the second derivative for y sub p. Now we are ready to plug the y sub p and its derivatives into the differential equation. So we simply put everything into the equation, okay? We're going to get a quite lengthy equation like this. So here, we have to be careful with the coefficients. You can see here, we apply the 2 to the last 2 terms, right? Okay. Now, we can just expand the products And then we try to find the like terms and combine them. So you will say, after we expand the exponents, we're going to say quite many different types of functions, right? So we're going to just combine them. For example, for the e to the negative t sine t, we have 3 terms. So we combine them here. And for e to the negative t cosine t, we also have 3 of them. So we combine them. So just to do the same thing, okay, for the rest parts. And we can get the simplified form like this. Now we can further simplify this equation by combining the coefficients. And you can see a lot of cancellations here, right? So in particular, for these 2 terms, the coefficients are all canceled out. And finally, we're going to end with an equation like this. So you can say for the first one, the 2a's canceled. You got negative 2b, right? For the second part, the 2b's canceled out. You're going to get 2a times of this. Once again, the third and the fourth terms, they get canceled out. And then the fifth term, the 2c and the 2c, these two cancel out. You got 1c left. And then you have the rest part. Now we just compare the 2 sides of the equation. We have to make the coefficients match, okay? So then you're going to say for the e to the negative sine t, you have negative 2b from the left-hand side, but you don't have it in the right-hand side. That means you have 0 of it. For the e to the negative t cosine t, you have 2a of it on the left-hand side, and you have 3 of it on the right-hand side. So you're going to see the second equation. For the e to the negative t, you're going to have c of this on the left-hand side and 2 of this on the right-hand side. For the t term, you're going to have 2d of it on the left-hand side and 1 of it on the right-hand side. Finally, from the constant, you have 2d plus 2e and 0 in these 2 sides. So we're going to get the equation system. Although here we have 5 unknowns, but you can say most of them can be solved immediately, right? So it takes just a little effort for you to get the solutions, right? And then we can just plug the coefficients into the proposed recipe, and you can get your particular solution. And then finally, we know the general solution to the differential equation is going to be a linear combination of the 2 fundamental solutions together with a particular solution, which is going to be this. Example 2. This problem is an initial value problem. So we have to first solve the equation and then use the initial conditions to determine the constant. So first of all, we have to solve the corresponding homogeneous equation. Once again, we're going to use the characteristics. So you're going to say in this case, the characteristic equation is going to be factorable. And then easily we can get the 2 roots are going to be -4 and 1. So that the fundamental solutions are going to be e to the -4t and e to the 1t. Now, when you check out the right-hand side, we notice that this is a polynomial, right? It has nothing to do with the fundamental solutions. So we can propose our particular solution as a polynomial of the same degree. And the next, we need to plug the y sub p into the equation to determine the ABC. And to do that, we have to first of all find the corresponding derivatives. But for a polynomial, it's pretty easy, right? So we know the yp prime is going to be twice of at plus b. And the yp double prime is going to be just 2a. So now when we plug this into the equation, we're going to get a quite neat form like this. And now we just need to combine the like terms. We have second degree, first degree, and the constant terms, right? Just combine them. You're going to get the equation like this. And now we compare the coefficients of the corresponding terms in these two sides. We're going to say for the t squared terms, you're going to say negative 4a in one side and 1 in the other side. For t, you're going to have 6a minus 4b in one side, and no t means 0t in the other side. And for the constant, you're going to have 2a plus 3b minus 4c, and 2 in these two sides. So we can just solve this equation system by substitution, right? You can say a is going to be obtained from the first equation, and then you plug it into the second equation, you can easily get your b. And then you plug your a and b into the third equation, you can easily get your c. Once we got the ABC, we can plug them into the proposal, and we got the particular solution. It's going to be a second degree polynomial like this. And it follows that the general solution to the equation is going to be C1, Y1, which is e to the negative 40, right? Plus C2, Y2, which is e to the t, and then together with the y sub p. Because we have initial conditions, we have to apply them to determine the C1 and the C2. So we need to find the derivative because one of the conditions is for the derivative. But this part is pretty easy, right? You just use the chain rule and the power rule. So easily we can find the y's derivative. And now we're ready to apply the initial conditions. So y of 0 is equal to 0 means when the t is 0, your y is going to be 0. So you simply plug 0 into the places of t, and then you're going to say a lot of zeros, right? So the non-zero terms are going to be c1 e to the 0 plus c2 e to the 0, and this constant, and then the y value is going to be 0. And for the second condition, you can do the similar thing, right? So here t is 0, and your y prime is going to be 1. So you can plug the 0 in, and here you're going to say a 0 term, right? So simplify these two equations because we know the e to the 0 is they are ones, right? So we're going to get c1 plus c2 is going to be 29 over 32. And then you can say the second equation gives you negative 4c1 plus c2 is going to be 11 over 8. For this 2x2 system, you can do elimination, substitution, or the inverse of the coefficient matrix, whatever, right? You feel comfortable. For example, if we do elimination, you can use the first equation minus the second equation, and you're going to say 5c1 is equal to, when you use this minus this, you're going to get this is going to be 44 over 32, right? So 29 minus 44, you're going to get negative 15 over 32. So now divide by 5, you're going to get negative 3 over 32. And then plug this into, for example, the first equation. You can easily get your C2 is going to be 1. And finally, we can get the particular solution to the initial value problem as this. You simply plug your C1, C2 into the general solution. Example 3. Once again, we have an initial value problem. So we have to first of all solve the equation and then use the initial conditions to decide the C. So here, for this equation, we have to first of all solve the homogeneous case. And once again, we're going to use a characteristic. And for this case, the characteristic equation can be again factored so that you can get the two roots are going to be -2 and 1. And then the fundamental solutions are going to be e to the -2t and e to the 1t. Okay, now we need to find a particular solution to the non-homogeneous case. And we need to address the two terms in the right-hand side. Well, for the first term, we notice that this actually is a fundamental solution to the homogeneous case, right? So usually to address this, we have to give an extra t. And for the second term of the right-hand side, this one has nothing to do with fundamental solutions. So we can just use a multiple of it. So therefore, the particular solution to the non-homogeneous case is going to be just like this. Once again, if you have something is already in the fundamental solution set, then you have to use an extra t there to address the term. So now we just need to find the derivatives of y sub p and then plug them into the equation to find the a and b. And for the derivative, you have to use the product rule for the first term. But this one is pretty neat, right? So you can say we just do the product rule. And we can get v sub p prime and v sub p double prime, right? And now we're going to just plug this into the original non-homogeneous case. And we can get the equation is going to be like this. And next, we're going to combine the like terms. We have e to the t's, and we have t e to the t's, and we have e to the negative t's, right? So just combine them. So you can see the e to the t's, we have 2 of them. T e to the t, we have 3 of them. And e to the negative t, we have 3 of them, right? So just combine them. And you're going to see some cancellations. And then you end with 3a e to the t is going to be 2 e to the t, so that you get 3a is 2. And you're going to get negative 2b e to the negative t is 1 e to the negative t, so you got negative 2b is 1. For the middle term, this is just canceled out. And then clearly, you can get your a is going to be 2/3 and b is going to be -1/2. Therefore, your particular solution is going to be just 2/3 t e to the t minus half of e to the negative t. Therefore, the general solution to the non-homogeneous case is going to be C1, Y1, which is e to the -2t, and the C2, Y2, which is e to the t, and then the y sub p. Next, we have to use the initial conditions to determine the C1 and the C2. And to do that, we have to find the y prime, because one condition is for the y prime. So here, for the first 2 terms, you can get the derivatives, right, directly. And then for the third term, we have to use the product rule again. And for the last term, we can get this derivative directly, right? And now we can apply the initial conditions. So the y of 0 is equal to 0 means when the t is 0, so you put the t is 0, you're going to get y is 0. And the y prime of 0 is 0 means, once again, when t is 0, so you put t is equal to 0 here, you're going to get your y prime is going to be 0. And now we use the fact that e to the zeros is 1. We can simplify the two equations as these two. And for these kind of equations, once again, you can use whatever method you feel comfortable with. Here, for example, if I do substitution again, okay, elimination again. So I'm going to do like the first equation minus the second equation, and then going to get 3c1 is equal to half plus 7, 6. So that's pretty much 3, 6 plus 7, 6, which is 10, 6, right? And the 10, 6 divided by 3, you simplify, you can get 5 over 9. And then you can plug the C1 into either equations, for example, the first equation, and then you can get your C2 is going to be negative 1 over 18. Finally, you plug the C1, C2 into the general solution, you can get a solution to the initial value problem as this. So that's all for this video. And thank you for